Hi, so welcome again. I'm Andrew Mills, a staff scientist at the Berkeley Lab and one of the co-authors of this report. Today, I'll welcome our speaker and moderate the question and answer session at the end of it. But before we get started, I wanted to go through a few housekeeping items. All the attendees in today's webinar are going to be in listen-only mode. So that means that if you have any questions that you have, to go ahead and please enter those via the Q&A box that should be on your screen. And we'll set aside about 15 minutes at the end of the presentation to go through and answer those questions. If there's any that we're not able to get to, we'll go ahead and try to follow up via email afterwards. If you have any logistical questions or anything like that, any challenges you're having, go ahead and enter those through the chat to me, and I'll try to monitor that and help out where I can. And again, as I mentioned, today's presentation will be recorded. We'll be posting a recording of this to our EMP website. Again, that site is shown on the front slide, and I'll go ahead and make sure that that's in the chat again here. It'll be the same site that's shown in the chat. And in addition, if you're interested, you can go to that link and access the report that this is based off of, and then the briefing slides that'll be shown today. So with that, I want to welcome James Hyungkwang Kim. James is a project scientist at the Berkeley Lab in the Electricity Markets and Policy Department. He conducts research on market policy along with the value and costs of power system technologies. Prior to the lab, James worked with Tanofska Power Systems. He also was at the Indiana State Utility Forecasting Group, and he also had previous experience working with the United Nations Environment Program. James holds a PhD in applied economics from Purdue University and has an MS in economics from Brunei University and a BA in computer science and industrial engineering from Yonsei University. So we want to thank James for presenting today, and welcome, and I'll turn it over to you.
Thanks, Andrew, and hello everyone for this webinar. And I'm James Kim, as Andrew well explained and introduced. I'm from Berkeley National Lab, and I'm working at the Electricity Markets and Policy Department and focusing on renewable issues. Today, I'm going to present a study that I've been leading, which is about grid-friendly PV, a project developer options to enhance the value of solar electricity as solar and storage penetration increase. I believe it is a very timely topic, and I hope it captures some of your interests, and I hope you can bring something back useful with you. And the multiple team members helped and contributed to this study, including Andrew Mills, as you already know, and the Ryan Weiser, Mark Bollinger, Will Gorman, and Krishna Montanus, and Eric O'Shaughnessy. And I also note that this study is funded by the Department of Energy, and you can find the link on the website and where you can download this slide, and you can also find the link to the Applied Energy Journal, where this study is recently published. So let's begin. This is the table of contents. I'm going to start with an introduction and motivation of this study. Then I'll explain about the framework to evaluate the grid-friendly PV options and more details about those options. Then I'll share the result of this study in 3 key categories. The one is shifting the timing of PV production. 2, maximizing the benefits of storage. And 3, enhancing grid services. And I will end this presentation with some of the key conclusions. So introduction and motivation. Why do we need a grid-friendly PV? Well, the previous studies and empirical data showed that with increasing PV penetration, the marginal value of PV decreases. And this is well represented in the data and the market situations in the US, especially in California. In this landscape, what project developers can do, I believe, is to make PV more grid-friendly so that it can retain more value while expecting higher PV penetration. As I said, we believe that this study is very timely since the solar will and is a major player in the deep decarbonization future, while the declining grid value of the PV can and potentially limit the attractiveness and the future demand. Also, the utilities and the PV power purchasers have been buying a product that is progressively less valuable. However, even then, we think that PV can be made more grid-friendly PV and retaining more value as PV penetration increases. But the important question is how? Of course, we're going to talk more about this, and this study is all about those details. Well, some of the necessary changes may include the modification to the PV project configurations and operations. And also, these changes can shift the timing of the energy production to the higher priced hours so we can retain higher value. If the grid-friendly PV is important, then what makes this study different? Well, the previous studies about grid-friendly PV options, they may not, and most of the time, they may not represent the rapidly evolving future landscape of the electricity market with higher PV penetrations. Many literatures assumed historical conditions with options that increase the grid value marginally, while some of the options even can reduce the total PV generation, which can be critical penalty, and we're going to talk more about that in the later slides. Also, some of the options, such as westward orientation, increase the value compared to the base PV plant. We'll also talk about it later. But how about less so when the PV penetration is higher, and why it is happening, and why some of the options increase the value compared to the base simple PV cases, but more so or less so when the PV penetration is higher. We'll go into and deep dive into the details in the later slide. And also, many of the previous literature focus on the standalone PV only, but not the hybrid is in the full picture. In contrast, this grid-friendly PV study reflects the continuously evolving the landscape with higher penetration of PV, and which changes and evolving the net load profiles of the markets and the electricity prices that essentially affect the PV grid value. And also, the hybrid is in the picture of this study in the full scale. The rapidly declining energy storage cost raised a lot of interest recently in solar plus storage hybrid plants. And those hybrid plants can easily shift the generation to the higher priced hours and more flexibly than the standalone cases, which is also going to one of the foci of this study. Also, in this study, we assume the PV plant can provide additional grid services, such as regulation reserves. And we conducted a comprehensive analysis of multiple PV configurations, as you can see on the left side. So the value is calculated using the PV generation profiles and the market prices, where the market price includes the energy price and the capacity prices. Also, the net value is going to one of the important metric, and to calculate the net value, we need value and the cost, because the net value is value minus cost. And for the cost, we use the present cost estimates of the PV and the energy storage to make the cost components in the picture. For the sake of the time, I'll save more details in this slide, and I'll leave the rest for the reference. But of course, we can come back to this slide when it's necessary. And this slides will be the introduction of the evaluation framework of this study to estimate the grid-friendly PV options. So this figure is the decision framework they used in this study that compares the grid-friendly PV options to the base PV plant in the same market with similar underlying cost components. I'm going to talk a bit of the base PV plants in the later slide while mentioning a few times this slide. So just bearing in mind, and we're going to talk more about the details of the base PV plants in the right after this. So as you can see on the framework figure, the y-axis is the value delta, the value difference between the grid-friendly PV options and the base PV plants. And the x-axis is the cost delta, is the same token, the cost difference between the selected grid-friendly PV options and the base PV plants. In this framework, the grid-friendly PV options with higher net value will be posited in the blue area, as you can see on the top left side, which represent the increased the value or relatively higher value and the relatively lower cost compared to the base case. And this is what we are looking for the grid-friendly PV options, and the vice versa for the lower net value area, which is in the red in the right lower side. This is not the desirable area because it has a lower value and the more cost compared to the base case. And comparing multiple PV options, this framework makes easy to distinguish a set of PV options having higher net value relative to the base case, because we just need to see where those options are posited in this framework. And this useful framework will be consistently used in this study throughout. So with that in mind, this is the base PV plant. Since we just mentioned the base PV plant a few times, this is more detail about this. So the base PV plant is designed to provide a reference point to compare it with the grid-friendly PV options. The characteristics of the base PV plant are set to be consistent with typical systems installed in the recent years based on the utility scale solar report reported by the LBNL and multiple other literatures. One thing to note is that for the purpose of this study, comparing multiple grid-friendly PV options to the base case, we keep the base PV at the very base level, such as the fixed tilting module, so they can be easily comparable to the other grid-friendly PV options that we want to bring to the picture of this study. And the detailed configuration of the base PV plant is on the right, like a standalone, the fixed module, south-facing azimuths, tilted at 31 degrees, and the inverter loading ratio of 1.3. And the inverter loading ratio is the DC rating and the AC rating ratio. So for example, the 1.3, the ratio means is that the DC rating is 30% higher than the AC ratings of the PV system. So with those, the base PV and the framework, here is a more details of the grid-friendly PV options that we're going to use in this study. So the first type is existing options that can shift the time of production to the higher priced hours with simple changes of the plant configurations using the readily available technologies like tracking or changing the azimuths or the other things. So for example, the tracking system can adjust the position of the PV array to track the sun, so it can generate more energy during the solar hours. And west-facing azimuths, you moving the PV array to face more on the west side, so it can produce more power in the higher priced hours in the afternoon, while maybe producing a little bit lower and less during the middle of the day. And the other existing options can be adjusting the inverter loading ratio, like higher inverter loading ratio, or higher or lower tilt, or even changing the location. And the other option is an emerging option that requiring emerging technologies, as it mentions, to shift the time of the production to the higher priced hours, or perhaps providing additional services for the additional revenue source. An emerging technology, a good example is a hybrid that collocating the energy storage to the PV system. The hybrid, as many of you perhaps already know, that can charge the solar energy produced in the lower priced hours and discharge them later in the higher priced hours, so it can attain the higher values. So we're going to have a deep dive of these options in the later slide. And the other example can be a vertical bifacial. So vertical, bifacial. So we can start with the bifacial and then we can move on to the vertical. So the bifacial basically means is that is a two-sided PV module. So it can generate the energy from the both side of the module compared to the, for example, like a monofacial can generate the energy only from the only one side. And the vertical bifacial is essentially means that tilting the bifacial module vertically and aligns on a north and south axis, so it can concentrating the production in the morning and the evening hours, like 2 hours of the day, and where the prices are tend to be higher. And the other option is an ancillary service provision, which we're going to also talk about a little bit more detail in the later slide, which can be an additional revenue source. And now this is a result section. And the first type of the result is the shifting the timing of PV production. The value increase comes from the changing the timing of the production to better align with peak system needs when the prices are generally higher. So, and when you face this figure, what is that? So how can we read this figure? The y-axis is the value delta, the value difference between the considered PV options and the base PV. And the x-axis is the cost delta. I think you're getting familiar with this framework, as I explained before, the cost difference between the PV options and the base PV. And the open dots, there are a lot of dots, but open dots represent the lower PV penetration year, which is 2012 in California ISO, and those results are based on those lower penetration year of the California. And the closed dots represent the higher PV penetration year, which is 2018 in California ISO market. And there are two figures, one in the left and one in the right. And the left figure is a combination of the base hybrid and the multiple standalone cases, which are kind of jammed into the little box on the left side. And the right figure is kind of zoom in of the little box on the left figure for the standalone cases only, so we can have a clearer view. So when you see on the left slide, our left figure, one thing is under outstanding, which is base hybrid option. The base hybrid is the energy storage collocated to the base PV plants, and it is just so much of the value boost. And when you look at the right side of the figure, we can also see the value boost among some of the standalone options like the west facing and vertical bifacial and tracking options. But you can also notice the scale difference of the y-axis, like the base hybrid, the value boost out of the base hybrid is far exceeding the value boost of the most of the and all of the standalone value boost options. But why is that? The standalone options, such as tracking and vertical bifacial, can shift the timing of the production as the base hybrid and energy storage can do. But the way that energy storage shifts the timing of the production from the low priced hours to the higher priced hours are far more capable and far more flexible. And it boosts the value a lot higher than the most of the standalone options do the similar things, but more in a more rigid way. And some of the standalone options like vertical bifacial and tracking and west facing, they are boosting the value compared to the base case. But one thing I'd like to note is that when you look at the west facing module in the standalone case on the right side, the orange dot, you can see something interesting is that it boosts the value, of course, during the lower penetration year and the higher penetration year, but it boosts the value more so in the lower penetration year and less so in the higher penetration year. In previous literatures and many of these studies says the west-facing module is touted to have a marginal value gain, but in this representation, the value gain of the west-facing module will likely to be diminished with higher penetration of the PV. But why is the case? I mean, some of the options boost the value and higher so with higher penetration, and some of the options like west-facing module boost the value, but less so with higher PV penetration. Why this contrast happening? And this slide is trying to answer these questions. It is because the impact of higher solar penetration on the grid field friendly options work differently depending on the way that the production is shifted by the option. Let me explain in more detail using this figure and pick up the base hybrid and the west facing so we can have a good contrast. But before that, the top figure is the generation profile of different options in megawatt hour. And the bottom figure is the market price of the different solar penetration years, as you can see on the bottom. And the winter and summer are differentiated. So you can look at the summer figure on the right side, and hybrid, the blue line, the blue dotted line, show the best responsiveness to align the production profile to the higher priced hours. I'll explain what that means. You can see a little hump of the time around like a 6 and 7 p.m. in the higher solar penetration year, and you can look at the bottom figure. The prices are peaking in the higher priced year around that time. So which means the base hybrid trying to, and it essentially does, shift the timing of the production to align their generation profile to the higher priced hours in the later afternoon of the higher solar penetration year. And the price profile difference, as you can notice in the figure, is that the higher priced year, the higher penetration year, having a peak pricing hours in the later time of afternoon, and it is happening around 6 or 7 p.m. and it is a few hours later than the peak price hours of the lower penetration. So that's how the base hybrid using energy storage responding these peak priced hours. But when you look at the west facing module, it cannot be aligned to the higher priced hours in the late afternoon. So what it essentially does is it look at the west side, so it can generate more energy during the later time of the afternoon, but it cannot just produce energy when sun goes down after 6 or 7 p.m. when the prices are higher. The sun is not just there during the higher priced hours, so the west facing module cannot do much. So what it means, overall, both the base hybrid and the west-facing PV can increase the value relative to the base case, while the way that the energy storage can shift the production from the lower priced hours to higher priced hours, it just makes a stark difference to the west-facing module. The way that energy storage is flexibly shifting the production hours is far more capable, far more better than the rigid standalone PV options, including the west-facing, which it tends to increase the value during the higher priced hours, but it has a limitation. It has its own rigidness. And that's what makes this difference. And with that in mind, the benefits and the capability of the energy storage, we are looking at the maximizing the benefit of storage. As we saw in the previous slide, the energy storage is highly capable and flexible to shift the timing of the production to retain higher value of PV. Because of that, because it is so flexible and capable, regardless of the PV subsystem profile, the output of hybrid plants during the higher priced hours, as you can see on, again, after 6 p.m. or 7 p.m., they are very similar to each other, because they're really responding to the higher priced hours in the later time of the afternoon. So the generation profiles in this figure on the top of the figure is the generation profile from the collocating the energy storage to the multiple standalone PV configurations. So when you look at the base hybrid is the base PV plus storage, and the tracking is the tracking plus storage, and the vertical bifacial is vertical bifacial plus storage, and so on. You get the picture. And why did we want to have a different PV subsystem configurations in the standalone module at the first site? It is because we were expecting that those standalone PV subsystem configurations can align their production to the higher priced hours, such as west-facing module and the tracking, and even some of the options sacrifice the overall production. However, when you're adding storage and collocating the storage to these standalone subsystems, because the storage act like a buffer to shift the energy to the higher priced hours, and because it is so capable and flexible, and this capability makes the underlying PV subsystem configurations redundant to the shift the timing of the production. As you can see around the 6 and 7 p.m. that all the generation profiles are kind of overlapping to each other. So what I'm trying to say is that initially you wanted to consider standalone PV option to shift the timing of the production to capture the higher value from the higher priced hours. However, when you start collocating the energy storage, and is more likely because of the declining cost of energy storage and the policy design, especially in the US. And the energy storage can do far better job to shift the timing of the production than the rigid underlying PV system configuration does. So those changes of the standalone PV system, especially sacrificing overall production, those configuration changes can be redundant and can even penalize when it sacrifices overall energy production. And it happens essentially. And with this background, we are going to jump into one of the most important part of this result. So because of the flexibility of the energy storage to shift the timing of the production and the redundancy of the PV subsystem to do so, the generation maximizing strategies with energy shifting capabilities of energy storage added hybrid can yield the most net value benefits at the higher solar penetration. And this is well represented in the figure. And I think I need to explain this figure a little bit more so we can be on the same page. This figure represents the net value delta, which is the difference between the value delta and the cost delta. So the net value delta essentially means the value delta minus cost delta, and where the value delta means, again, the value difference between the PV options and the base case. And the cost delta, again, I think you're getting used to have this picture, is the cost difference between the PV options and the base case. So the net value delta is the net value difference between the grid-friendly PV options and the base case. So what we want to have is a positive net value delta, of course. So the more right side of the figure is more desirable. And as you see here, the base case on the bottom of the figure with the gray dot is anchored at 0. And the gray circles, like a base case and the many gray circles hanging around like a 0, those are from the standalone cases. And the blue triangles, like scattered in more diverse scale, those are from hybrid cases. And the open ones, again, the open circles and open triangles are from the lower penetration year, and the closed ones, closed circles and closed triangles, are from higher penetration year. And the hybrid case, as you see on the triangle lines, each case having 2 lines. The one is the upper bound, assuming the perfect foresight of the real-time prices and solar penetration, and the lower bound assumes the imperfect foresight of that. So I'll give you a specific example. So when you see the tracking on the second from the top, there are standalone solar with circles, and both circles are located in the positive net value area, which means positive net value delta, which is great because that's what we want. We want to have a positive net value delta, and which means the both of the higher and the lower penetration year of the tracking standalone tracking having a positive net value delta compared to the base case, and more so in the higher penetration year. When you look at the tracking hybrid, the two lines connected by the triangles, and the upper one is the perfect for site, spanning from the negative net value to the positive net value delta, which means it has a negative net value delta in the lower penetration year, while positive net value delta in the higher PV penetration year. So what we can see from this figure is that the net value ranking, the one is that the net value ranking of PV options with storage, which is hybrid, is quite different from the ranking of the standalone PV options. Like, IRL 1.7 was not in the prominent option in the standalone cases. And these differences are coming from both the value and the cost side. The value delta of these multiple hybrid cases are generally coming from the energy storage side, where the energy storage can shift the production from the lower priced hours to the higher priced hours. And if the underlying PV system can generate a higher energy production, yeah, it can have additional value out of that. And the cost delta and the cost side difference are generally from the overall production profile of PV system. So when you see the lower ranked options in this figure, you can notice that those are generally the options having a overall lower energy production. So which means less megawatt of energy and less hours of the production. It is harder to spread out the cost added by storage. And the energy storage cost is getting cheaper and cheaper over the years, but it's still quite cost heavy equipments. And when you have a lower megawatt of the production, it is not easy to spread out those costs across the lower megawatt of the production, as you can see in the lower ranked options in this figure. So with that, the PV subsystem that sacrificed the overall production to better align solar generation profile to the higher priced hours becomes less attractive and even penalizing when collocated with energy storage. And a good example can be a west-facing module. In contrast, as you can see at the top lines of the figures, like DC couple 1.7 tracking, inverter loading ratio 1.7, those options that increase the overall production and the PV subsystem that increase overall production, that is becoming more attractive. For example, the 1.7 inverter loading ratio was not an attractive option. As you can see, the circles in the standalone cases, they are almost overlapping. But since it increased the overall production, it becomes an attractive option to consider when collocated with energy storage. So the best net value gain on the top line, as you can see, is from the generation maximizing strategy, the DC coupled 1.7 inverter loading ratio plus tracking hybrid system. So now let's move on to the other category of the result, which is enhancing the grid services. One of the options to enhance the grid service is providing regulation services in the standalone PV. PV plants can provide regulation services using the advanced control capability. And this technology actually exists today, and the cost of adding this control is quite insignificant. So the standalone PV using this technology can provide a regulation by taking the portion of the PV energy generation to provide the regulation services when the regulation prices or the ancillary service prices are higher than the energy prices, and also the high enough to make this trade-off of energy and ancillary service provision. And this figure represents the 7 ISOs of the case standalone PV provide the ancillary service. And the value increase is generally modest across the markets. And it varies across the years and regions, and it's quite sensitive to the market condition changes. One thing to notice that we only counted standalone cases that provide the energy, the ancillary services in this study. However, the good news is that the parallel project is forthcoming, and that project is more deep dive on ancillary service provision from both the hybrid and standalone cases using multiple configurations and assumptions and sensitivity analysis. So please stay tuned for this study. And the other option is changing the location. So if your currently installed PV plants are not in ideal location and it's not in the higher priced regions, you can move it to the alternative site with higher price, which means higher value. So this figure essentially represents the market specific net value delta of thousands of the locations in 7 IS LTOs in location specific net values. And you see blue and red, and the red areas are the ones having higher net value, and that's what we are looking for. As map represent, the grid value varies with locations due to great situations of the market, and the location of prices happening even within the market. So the prices are different in different locations of the market is because of the transmission line constraint, because the capacity is limited and the congestion happens and it separates the price in the different regions. So we have all 7 markets in the map, but how can we look for the opportunities? So the one way is the contour lines below the map can be helping. So the x-axis, again, I think is becoming redundant actually. The cost delta, the cost difference between the PV, the locations and the base PV, and the value delta is the value delta in the y-axis. So when you look at the contour lines, it seems like a KISO, SPP, and PGAM, they're kind of like a drawing under the more cost and less value type of regions. But when you look at ERCOT, MISO, and NISO, they seem a little bit more promising because they have more areas in the higher value delta region in the contour plot. So for example, like most of the red dots in ERCOT market are in the western region, which we can easily assume, it may be correlated with the wind power, and many of the red dots again in the south areas like, load pockets and the population areas. And also NISO has a lot of positive regions. And when you look at the map, many of the red dots are located in the Long Island. Yeah, this is a Long Island. So even though the Long Island region has promising signal, it has a positive net value delta in this analysis, but it may not be practically possible to build like a lot of PVs in the Long Island. So there are a lot of more constrained to build a PV in the Long Island compared to the other regions. I think this message conveys and connecting to the other options that we introduced in this study. So the economic signal can tell us something that is desirable action or options to take, but some of the realistic constraint may not enable that to be happening. So we want to make a note as one of the things that we should keep in mind. So the conclusions. The PV standalone options, as we've seen in multiple slides before, it can help to maintain the PV's grid value, but the net value is usually quite marginal and it varies with solar penetration level. And even some of the options can have higher value boost and lower penetration, while it's not the case in the higher penetration. And the west-facing module can be a good example. And we also look at the hybrid. Adding energy storage to the standalone PV configurations can alter the cost and value dramatically. And the strategies that shifting the timing of PV generation, especially at the expense of the total generation result, and potentially a penalizing the value gain. Also, these strategies of changing the timing of the production of the standalone module can become redundant when you add energy storage that is far more capable and flexible to shift the energy production. In this regard, strategies that maximizing the PV generation can provide the largest net value gains when you combining the energy storage in the picture, especially at the high PV penetration feature, which means essentially the generation maximizing strategies today can yield increasing net value benefits in relative term, especially when we are expecting the higher PV and the storage deployment in the near future. Overall, I hope these findings can help and aid stakeholders who are seeking to achieve higher solar penetration in the deep decarbonization future, which we are, I believe, heading into. So this is the end of the presentation, and here is the contact details. So please contact us if you have any additional questions or comments, even after the Q&A session, or any other comments or note. We will welcome to have your emails. And I think this is it, and the Q&A session can start, I think, just now. Thank you.
Great. Thanks so much, James. And we really appreciate the great questions that have been coming through on the Q&A. Please do continue to add your questions to that. I think a few of these we'll try to respond to. I think just even raising the question itself in some cases is interesting. So we'll start going through those. So let's start off with a little bit of discussion of the PV subsystems. So one question just to begin with was, why not east-facing vertical bifacial in the morning and west-facing vertical in the afternoon? And also with the bifacial vertical, they've been seeing it stowing in winter at sites with extended ground snow cover. And then you see some generally higher cloud conditions where you see some significant production boost relative to the normal tracking. So just a little bit more maybe about the vertical bifacial and how that works, and maybe some of these comments about the snow cover.
Totally. So yes, so this is, I believe, some of the helpful slide for about the bifacial, vertical bifacial, and the east facing and west facing on that matter is that the west facing is tend to having a higher generation profile in the afternoon, which is aiming to capture the higher priced hours in the afternoon. And why not east facing? And when you have an east facing module, I believe you're trying to generate more during the morning hours, and that is trying to capture the prices during the morning time. But when you see the price profile on the bottom figure, it tends to have a higher prices in the later time of the afternoon rather than the morning in morning hours, especially in this price profile. So if you're in the area that especially having a higher prices in the morning, and that's currently and commonly observed, then east facing can be a good strategy. But I think the most of the electricity market, especially the California market that we are concentrating on, is showing this price profile. So why not vertical bifacial in the winter? I think, in general, this is the California market that we're focusing on. So the snow is not fully in the picture. And one thing I like to note is that, of course, you can go to the slide and download it and see the appendix, but we have some sensitivity analysis having the structure and the framework and the same options compare, not just in California, but also the other markets like ERCOT and the regions and markets in the US. And this result qualitatively and quantitatively aligns to the result that we are having from the California market, which means this result of the standalone and the hybrid is easily translated and transferable to the other markets. So I like to note for that matter. I hope that answered your question.
Great.
Yeah.
Okay, and then we have another question. So it says thin film solar can have a wide angle of acceptance, meaning that light coming from a wide angle from normal can be harvested efficiently. There's a thin film technology which has a higher efficiency than today's commercial solar panels, yet much lower cost per watt. It can be laid flat side by side for greater surface coverage than tracking can, especially during peak production hours. So thus with storage, you can get the benefits of time shifting without the cost of tracking. And then the question, which I think is a great comment, so thanks for that. And then just sort of the question is can we give a quick estimate for the net value of doing that? I'm not sure if we can.
Yeah, okay, so just a quick comments. I think yes, the thin film solar, I think I'm not fully like knowledge and expertise in that domain, but I believe the thin film solar can have the benefits as mentioned in the comment. And having a value and the cost estimation, especially the net value delta, and comparing to the other options, I think in theory that is not impossible, but I like to say it is not like widely accessible and very handy, so we can just click some of the buttons and compare those options very easily. I think it is not the case to be ready, but yeah, but that is definitely interesting to take a look at.
Great. Okay, and then we had a couple of questions just about ILRs. So one of them was just, were there any other ILRs modeled? Questions about what the net value delta might look like with. So let's start with that. With just were any other ILRs modeled, and then did we come across anything that talks about higher ILRs over 1.5 requiring special design consultation with the inverter manufacturers? Because that might avoid warranties.
Right. So that's a great question. So we design the different types of ILL, like a lower and higher than 1.3, which you can see that one of the example is the higher inverter loading ratio, which is 1.7. So we designed them. And the reason that we didn't really show the full picture is because, we don't want to clutter the figure, but more importantly, as you can see on this figure, the standalone solar result for the inverter loading ratio 1.7, when you compare the lower penetration and the higher penetration and where it's located, it is essentially not too different from the base case, and it doesn't have a significant meaningful difference between the lower and the higher penetration case. So because it is less interesting, so we intentionally decided to simplify the figure by not showing and representing all the difference of ILR 1.1 to 7, 3, 4, 5, 7. So this is a selected choice for the presentation matter. And yeah, like over 1.5 and is a warranty, I think we are not fully considering that aspect in this study specifically, but also I am aware, since the recent, especially the recent installation, the current trend is increasing the inverter loading ratio higher and higher, and quite commonly seeing like over 1.5 cases in many of the regions in the US. And that's one of the reasons that we chose the 1.7 IRL to represent some of the higher inverter loading ratio. But if the warranty is something to be considered in some of the cases, yes, definitely that can be a concern. And I hope like individual project developers and they have a better local knowledge and what they're facing into. But definitely, if that can be an issue, then we can consider that.
Okay, so now we have a couple of questions getting more into the hybrid side of things. So to begin with, are we showing here at all that DC coupling is more attractive than AC coupling? Is that what this result is showing anywhere?
Yeah, so Yes, so I think the DC coupling. So I cannot speak about like all the general cases, and just to be noting, I think these like sensitivity analysis of the AC versus DC and the different like configurations is a more detailed study that coming out of the LBNL. And you'll find them pretty soon, so please stay tuned. So we have a study that having more deep dive into some of the different configurations of the hybrid and comparing its value and the net value delta in different configurations. So in this study, we intentionally chose a one specific PV subsystem case, which is DC couple 1.7 inverter loading ratio plus the tracking. And it definitely like combining of the all good things of higher inverter loading ratio and the tracking and DC coupled. And yes, DC coupled in this case, basically showing the higher value boost is because, when you look at the AC and DC, the energy that the energy storage can charge and discharge, which it can handle for the shifting the production is higher than the ACE case. And yeah, and this study is more of comparing the different options, but not really like a deep diving into a different multiple configurations of the hybrid. And I like to note once again, there is a separate hybrid study at the LBNL that's studying more of this aspect, more detail.
Great. And then just again, to help understand the hybrid section, what was the size of the battery relative to the PV? And I guess also what was the duration of that in this? And how would different ratios of PV to battery size affect the overall plant value?
Sure. So the energy storage, the size is the half of the PV capacity, so the 50%. And the duration of the choice in this study is 4 hours. And I believe, yes, the choice of the parameters like the capacity and the duration can affect the numerical result. However, again, we have a detailed hybrid study that I participated using the different configurations. And I like to say with confidence that change the parameters, like probably 2 hours or 4 hours or 50% or 75% of the energy storage will not change the overall and main result of this study meaningfully, which means the qualitative order and this result of this hybrid and comparing the options will not be significantly changed by different parameters with sensitivities. So yes, so those different durations capacity will change the value numerically, but not qualitatively of the overall result.
Okay, and then along those lines is how sensitive might be the results that we have to different storage cost assumptions, and if you could say anything in particular about what our dollar per megawatt or dollar per megawatt hour assumptions were for the battery system costs.
That's a great question. So and I think luckily I have an answer for that. So I think I briefly mentioned that this net value delta is the value delta of the cost delta differences. And the value delta is coming from the energy storage and its capability of the energy storage that's shifting the energy generation from the low priced hours to the higher priced hours. And the cost delta is I think the question is aiming at the cost delta. And if you change the assumptions of the energy storage's cost, and it would change the cost and the cost delta of adding energy storage consistently across the different options. So one easy answer is that if you change the assumption of the energy storage, it will kind of shift this net value delta from left to right, from right to left, depending on how you scale up or down the cost, but it will not change the order and the qualitative, the ranking and the result of the different options that are presented in this figure and the result. So yes, the cost assumptions will change the value numerically, but again, it will not change the overall picture. But yeah, but and I think one of the common complaint of the cost assumptions of the energy storage is that some of the reports and some of the institutions, they're tracking the energy storage cost. And I think the cost in this study is reflected a little bit higher than the energy storage cost today. And the one reason is, the landscape of the and the speed of the cost reduction in the energy storage is very, very fast. So some of the report and the institutional the parameters of the cost assumptions is not really keeping up with them. So bear that in mind. But that's a great question. So thank you.
There's a couple more questions that are on the hybrid configurations, but maybe before going into those, we can just talk a little bit more about some of the other aspects of this. So one of them was on the location side is, doesn't Long Island point us to using rooftop and canopy over parking lot type installations to take advantage of that net value that's available in the Long Island area? And that the canopy can be fairly low cost with thin film and advanced structural systems.
Great. So I like to hear once again the thin film and this kind of like a distribution side of the aspect of having PV on that matter. So yes, I think that's a great idea. And please feel free to analyze those aspects of the Long Island, and if you find the opportunity, I believe that's a boon for many developers. But one thing to note is that I think many of you probably aware, but probably I was not clear enough, that this study is focusing more of the wholesale side of the large scale PV that installed in the bulk scale, participating in the wholesale electricity market. So yes, the Long Island in this map and our analysis showing higher net value delta compared to the other regions. But since we are focusing more on the wholesale side of the aspect of the PV, and since the Long Island relative term having a more constrained space in the residential areas to install this large scale PV compared to the other area, I think that aspect is something I mentioned when I was talking about the Long Island. But definitely, I mean, if you're seeing more opportunistic chance to install the thin film in the parking lots or garage or rooftop, and if you think you can gain more value, I think that's a lucrative opportunity.
Great. Okay, and then just some questions on sort of some of the basic methods. So this question is primarily about where we get our market prices from, and do those market prices vary by market, and talking a little bit about whether we're using nodal or hub prices.
Sure. So I think this location map can be helping. So the prices are from the hub that is located near to the centroid of the currently installed PV. So it basically means you considering all the PV locations and its capacity across the markets, and they have a market specific centroid of the installed PV, and we are looking for the hub of the representing hub in the market. So that hub prices are the used prices to analyze this study. For example, the CAISO is SB15, and the other markets, they also have a representing hub for the prices. And the exact the hub and the locations that is in the appendix of the slide, which you can download using the link that is present in the chat box.
Great, and then just one final question before we wrap up here. It's just, again, going back to the inverters, was when we were talking about the PV capacity that we were doing, is that the DC rating or the AC rating, and is our battery size dependent on the ILR at all?
So yes, so it is an AC side, and the battery side is a co-location. Of course, yeah, we are aware there are multiple ways to adding the energy storage to the PV system, and and we have a co-locating the energy storage. So the IRR, as you saw in the previous figure, that the IRR changes the 1.7, which is higher than the base hybrid, and the base hybrid assumed having a 1.3 inverter loading ratio. So the inverter loading ratio with 1.7, which is higher than the base case, is having a increased annual production, and increased annual production, it connects to the higher value especially when you're adding the energy storage. So it is an AC side, and having a different inverter loading ratio, especially the higher one, is increasing the net value delta when you add the energy storage. I think it answered the question.
Okay, well, great. And I just want to remind everyone that there were a few more questions we didn't quite get to that had to do with some of the assumptions on cost and sort of the basis for some of those. And I'll point you again to the report that's available on our website that does have some tables that go into those and a little bit more of the references and so on. We'll also try to follow up by email directly to some of those questions. But just wanted to thank James for a great presentation and for all of you for participating with the questions and answers. I thought that those were really great questions and some really interesting points that were brought up during that. So appreciate your time, and we'll look forward to doing another webinar with you all sometime soon. And have a great rest of your day.
Thank you, everyone, and thank you, Andrew.